Hi, I'm Umnik. I will be doing first round 1056, second division, and I will try to explain what I'm doing along the way. Yeah, I'm sorry in advance. I have some issues with my voice today. Hopefully, I can speak for 2 hours. Problem A, el fucho. Do all the problems have names in some Spanish or something? Okay, I guess not. So I will not have to pronounce any more words I do not know how to pronounce. Well, probably I will still have to. Okay, problem A. Juan and his friends are going to split themselves into N teams and play a modified double elimination football tournament consisting of a winners group and a losers group. Initially, all teams belong to the winners group. In each round of the tournament, the following happens as long as one of the groups has at least 2 teams. All teams in the winners group pair up. If there is an odd number of teams in the winners group, there would be a team that didn't get paired up and wouldn't play a match. That team stays in the winners group. For teams in the winners group that got paired up, each pair plays a football match in which there are no ties. If a team wins, it stays in the winners group. If a team loses, it drops down to the losers group in the next round. All teams in the losers group pair up. If there is an odd number of teams in the losers group, there would be a team that didn't get paired up and wouldn't play a match. The team stays in the losers group. For teams in the losers group that got paired up, each pair plays a football match in which there are no ties. If a team wins, it stays in the losers group. If a team loses, it gets eliminated from the tournament. More or less normal double elimination, except I think in actual double elimination, for one tour in the winners bracket, there are 2 tours in the losers bracket. I think, not exactly sure. Uh, yeah, that seems like not exactly the same, but fair approximation. Note that in the above process, when a team loses a match in the winners group, it drops down to the losers group in the next round. That means it is not considered for the pairing process in the current round's losers group. Well, you could have swapped the order of those 2 things, and that would be fine. After multiple iterations of the aforementioned process, both groups end up with a single team each. When this happens, both teams face off each other in a match and a victor emerges. Determine how many matches were played in total. It can be proved that no matter how the teams are paired up and which ones win and lose, the answer remains the same. Well, yeah, because the we only care about the number of those things, but also there is a much better solution than just implementing all this. You can just write what is written in the statement, maintain number of teams in the winning bracket, number of teams in the losing bracket, and do rounds one by one. It will converge in logarithm number of iterations, and n is small, so even you can even do it one by one. I don't know, in often. But you can actually solve this problem in constant time by understanding how double elimination tournaments work. The whole idea of double elimination is that each team, to be eliminated from the tournament, you need to lose twice. You first lose in the winners bracket and go to the losers bracket, and then you lose in the losers bracket and go home. So among our n teams, there will be one team that stays in the winners bracket. That team loses 0 matches. There will be one team that stays in the losers bracket. That team lost 1 match to go from winners bracket to losers bracket, and that's it. And all other teams are eventually eliminated. So each of those teams lost exactly twice. Well, the thing is, the number of matches is the same as the number of losses in those matches. So the number of losses is there is one loss for the team in the losing bracket and two losses for the n-2 teams that got eliminated. So that's 2n-3. And there is a final match, so the answer is just 2n-2. So you read n and print 2n-2. Problem B. Abraham's Great Escape. Abraham is a brave explorer who goes where no other programmer has gone before. For his next expedition, he plans to investigate a peculiar maze. He knows that the maze is an n-by-n grid with an arrow in each cell that points in one of four directions, up, down, left, and right. Abraham also knows that if he stands on an arrow, he will be forced to follow the arrow starting from that cell. Each arrow moves Abraham exactly one cell in the direction that it is pointing. If he reaches an arrow that points towards the outside of the maze, Abraham will escape the maze. Abraham doesn't know how the arrows are arranged, so he wants to plan for multiple scenarios. He tasks you with finding an arrangement of arrows in the grid such that there are exactly k starting cells from which he can escape the maze. Okay, so this is a constructive problem. We are asked to construct n-by-n grid of arrows such that for each starting cell we will follow the arrows and if we eventually leave the grid, this cell is considered good, and we want to construct a matrix where there are exactly k good starting cells. Well, it feels like we should be able to like draw some kind of cycle that goes around the cells from which we do not want to escape. Or I guess not even cycle. We can have just in the top left corner we can have two arrows that look at each other. If we arrive at one of those, we will go between them infinitely. And then if we need more cells from which there is no escape, we will first like continue in the first row, pointing the arrows to the left so that we reach that inescapable corner. If we need even more than the first row, like we will go to the second row and like from there try to go up. So we will go to the first row from which we cannot escape. Then when the second row is full, the same for the third, and so on. So we will fill up the number of cells that is from which we shouldn't escape, and then from the rest we will just point the arrows down, and like from each of those cells it goes straight down and we escape. To do that, we will need to have at least 2 cells from which we shouldn't escape. So if k is at most n square minus 2, then this works. If k is equal to n square, then we should escape from every cell, so just go down from every cell. But if k is equal to n square minus 1, that's impossible, because there should be like exactly 1 cell from which you shouldn't escape, but from that cell you have to go somewhere, and from that cell you do escape, because from all other cells you have to escape. So that is impossible, and like that is what's happening in this third example. You can see that k is n square minus 2 minus 1 here, so the answer is no. Otherwise it is always possible. There was a very simple problem somewhere recently, like I think it was 0 stage of the first season of the Universal Cup. There also was a problem about like constructing a maze with those arrows, but I think in that problem yeah, you needed to construct a maze such that you always reach the top right corner, and you also had given number of arrows to put in the maze. That was a nice problem. A bit harder than that, but also not very hard. Okay, so if k is or rather, let's calculate the number of cells from which we shouldn't escape. If it is 0, we need to do something special. If it is 1, then it's just impossible. And otherwise we have the main solution. If it is 0, then we just put all the arrows down. And if m is at least 2, it is possible. First we print right left, then iterate over the rest of the first row. If we still have some cells from which we shouldn't escape, we go left, otherwise go down, and when we go left we decrease the number of cells from which we need to escape, and now iterate through the rest of the rows. So if I don't want to escape, I print up, decrease m, and I also need to print the line breaks. Left, up, and then down. That's 5. It looks good to me. Problem C is ancient wizards' capes. There are n wizards in a row numbered 1 to n from left to right. Each wizard has an invisibility cape which can be worn either on his left side or on his right side. Harry walks from the position of wizard 1 until the position of wizard n. What a weird place for the limitation on n. It's not the first occurrence, but it's here. And registers how many wizards he sees from each wizard's position. A wizard in position J is visible from position I if wizard J wears his cape on left side and J is on the left. Okay, so we do not see wizard if his invisibility cape. I think in Harry Potter it was invisibility cloak. If its invisibility cape is like closer to us, like it's between us and him. And we always see the wizard in which position we are standing. In particular, note that wizard I is visible from position I. Okay, yeah. Harry's list is very old, but after much work you managed to decipher it. What are you talking about? What list? I guess the numbers, like how many wizards are visible from every position, are on the list. Okay, the list is an array A of n elements where ith element is the number of wizards that Harry saw from the position of wizard I. Task is to determine how many of all possible cape arrangements that Harry could have seen are consistent with the data recorded by the list, modulo some weird number. Isn't it like more or less unique, no? Okay, it's not exactly unique, but okay, so we have an array of integers, how many elements are visible from position I, and we need to calculate the number of possible arrangements of L and R. So if we have something like this, for every position we're counting like 1 for this position plus number of L's on the left plus number of R on the right. So 1 plus L to the left plus R to the right. So for this array it would be 4, then again 4, 1, 2, again 4, or is it? Yeah. 2, 2, 1, 5, 3, 1, 1, 5, and then 4. Okay, so what I want to say is that if we look at two consecutive elements, they're not very different, right? Like for example, if we are looking at those two elements, for the positions that are not coinciding with one of those two elements, they're counting the same thing. So if we look at the difference of those values, what is AI plus 1 minus AI? So for those positions, they're counting exactly the same thing. Then both of them will add 1 for the position where they're standing. So those will cancel each other out. But also this one adds 1 if this one is L. So we add 1 if SI is L. But we subtract 1 if this one is R, because when we're standing in position I, we will add 1 if this is R. SI plus 1. So okay, so those things are this is 0, 1, this is 0, 1. So those values can be minus 1, 0, or 1. Let's look at like the possible values of the characters corresponding. So if it's minus 1, then this must be 0 and this must be 1, so it is RR. If it is 1, then this is 1, this is 0, so this is LL. And if the difference is 0, then it is LR or RL. So if the difference is 0, then the values change. If it's minus 1, then both of them must be R. If it is 1, then both of them must be L. So what that means is that just by looking at the differences in the arrays that are given to us, if some differences are greater than 1 by absolute values, then the answer is just 0 right away. If some differences are 1 by absolute value, then we know both the characters, like on positions I and I plus 1. So in our string, so we want to calculate the number of strings that are consistent with the given array. We will have some pairs of positions that are already fixed, for example LL, LL, R, something like that. Here we don't know what is happening yet. Also, those pairs can intersect if we have like two neighboring differences that are both non-zero, then the pairs can intersect. If they say the same, then fine. If they say different about the same character, then the number of ways is obviously 0. So we might have some pairs. Also, do not forget about the case when we do not know anything. But in any situation, if we do not know anything about one character, it means that both differences here and here are zeros, which means that that character must be different from both its neighbors. So if we have at least one pair determined, then actually it's all uniquely determined, because from that pair we can go left and right and determine all the positions that were not determined yet. So for example, here we know that this character must be different from this one, so it's actually R, L, R. And they will alternate like this. And here, for example, if there are 4 characters here, or even number of characters, we will see that that's actually incorrect, because those 2 characters also must be different, but that's not the case. But in any case, we can determine the only option it can be, and then we can calculate the actual array by this formula, and compare it with what we have initially. And yeah, don't forget about the case where we don't have any information. So we don't have any pairs that are non-zeros, so they all must all be zeros, which means that all the elements are alternating, and if we fix the first character, then it will alternate till the end, so we can check those 2 options and see if any of them are correct. Add 1 to answer if yes. So the answer is actually at most 2, and 2 can happen only if all the numbers are the same, so all the differences will be 0. I don't know if it can actually happen. I think there were some cases when the answer is 2. Well, okay, yeah, for size 1 the answer is 2, and here the answer is 2. So I guess if n is odd, then it can be 2. But it's probably you can say more about the structure, but it is easier to just construct all the options that are viable and then check if it is correct. I think it is simpler to just iterate over the first character right away than get the information that we can get, and then just check if it's all good. So I'm saying let's fill the array with -1s, which means that I don't know anything yet. Then I will say that the first character is something fixed, which I'm iterating over. And then if it corresponds to an actual correct option, I'm increasing answer by 1. How do we like, now that I know that my leftmost character is fixed, I can just go left to right and fill in like the characters left to right. I'm looking at the difference. If the difference is 0, then I need to set the character to the like opposite of what it was before. So bi is bi is bi minus 1 XOR 1. If it is greater than 0, I said that if it is at least 2 by absolute value, I can just return false right away, but it doesn't matter. Like, I can say, okay, for positive I will set something, for negatives I will set something, and then I will check if everything is correct. So for positives, I was saying that if it is positive, then it should be left. So let's say that left is 0. Okay, so for every position I want to count 1 plus number of zeros on the left plus number of ones on the right. You can like use like some prefix and suffix sums, for example, or you can just maintain that value while doing a kind of scanline. I will choose this option. So when I'm staying at position 0, my value is 1 plus the number of ones to the left, which is like everything except the 0's position. And when I move from 0's position to the first position, if it is 1, then it counted for the previous position but shouldn't now. So I need to do minus minus. And if the previous is 0, then it didn't count on the left before but should now. So it's v plus plus, and if ai is not v, return false. Otherwise everything is good and we return true. So it's correct answer. It is not exactly what I was saying before. I was saying like that if the difference is non-zero, we can determine both left and right, and like there can be intersections of those known pairs that they can contradict each other right away. But like you can solve it like this. But since I still will need to iterate over the first character in case I don't have any known pairs. At least if I want to like solve it like this. I said, well, okay, let's just iterate over the first character anyway. Like that just multiplies running time by 2. But now it is much simpler to construct the only possible option with the fixed first character, and we do it with like one simple for loop from left to right, and then check if it is correct. And it's like one of the things that I think I do well is thinking ahead about the code I will write, and like taking my time before starting to implement to think like what I can do easier. You don't have to make a solution as fast as possible if it has like correct complexity. Sometimes you can like allow your computation to do more with like if it allows you to write less code, and it is like less complicated, less prone to having mistakes. And like I thought, okay, so I could analyze it more and not check options, like not construct actual array and then check them. But constructing actual arrays and checking them is easy. And then I thought, okay, I will have to iterate over the first character in one case, so let's just always iterate over the first character. It's just 2 times slower, which is nothing because like solution is linear. So I can totally afford it. And it will make the implementation so much simpler. And I just thought right away, okay, I'm switching to that way of implementing because it will be easier to write. Problem D, batteries. This is an interactive problem. There are n up to 40 batteries numbered from 1 to n. Some of them work while the others don't. Let A be the number of batteries that work. It is guaranteed that A is at least 2. You're given n but not A. A is the number of batteries that work. Okay, so we know how many batteries we have, but not how many of them work. There is a flashlight which can hold 2 batteries, and it only turns on when both batteries work. The batteries have been shuffled, and you don't know which ones work and which ones don't. You can choose 2 batteries and try them in the flashlight. You want to find a pair of batteries that work, however, you are worried about breaking the flashlight, so you want to limit the amount of trials you attempt. Therefore, you should find a pair of working batteries using at most n squared divided by a rounded down trials, and we don't know a. And the interactor is adaptive. Okay. So as soon as like this is actually not an interactive problem, right? Like we do not get any information basically. We try in pairs and we get responses. It's not working, not working, not working. Once it is working, we are done. So we just need to get the list of pairs we want to try, and like make sure that it works fast enough. Um, Maybe just do something dumb, like so we have some batteries. Okay, I marked 8 of them, which is not a great way to to showcase my idea, but well, okay, let's add some. Now we have 11. So what I would try is let's try like splitting them in pairs and checking those pairs one by one. If one works, great. We checked like most n over 2, which is smaller than n squared divided by n even. And n is at most. A is at most. So we have n squared divided by a rounded down thrice. So like if we have a lot of working batteries, we need to find a working pair fast. But if we don't have a lot, we can have a lot of tries. And like if A is 2, we have just 2 working batteries, then it's okay to try every pair. Moreover, there is no strategy better than trying every pair. But like the number of pairs is n times n minus 1 divided by 2, but we have n times n divided by 2. Rounded down, but it's still not less than n times n minus 1 divided by 2. So if a is 2, it's fine. So basically, what I'm trying to do here is check those pairs. If one of them is working, then great. If none of them are working, it means that in every such pair there is at least one not working battery, which means that A is less, like not greater than n over 2, well, rounded up. Like, we will look at exact numbers later. So that means that like A is not very big. So like the greatest A can be is n, which would give us n tries. If we now know that A is at most n over 2, then we have like 2n tries, roughly. So what I want to do now is like take those pairs and unite them in even bigger sets. Also, like we had odd number of batteries here, so this one was left. But we can like say that let's just unite this pair and this lonely one. We will have a triplet. And now in every such group, I will just try all the combinations. I will not try again the combinations I already tried. So like those two are already checked, those two are already checked. But now I will check like first and third, first and fourth, second and third, second and fourth, and so on. What would it mean if I didn't find any answers here? That would mean that in each group there is at most one working battery. And that means that the number of working batteries is like roughly bounded by n over 4 rounded up. But how many tries did I do? So in if n is divisible by 4, let's say for now, let's say n is 4k, then I will have k groups of size 4, and in each such group I will do 4 times 3 divided by 2, which is 6 number of tries. So I did 6k tries, which is 1.5 times n. But I knew that I have 2n tries, so I'm still certainly good on the number of tries I had. If I found one working, great. If I didn't, let's continue doing that. Let's take those pairs and unite them even more, and so on. So after some iterations of that, like most of my groups will be of size like power of 2, and then I will have last group which is smaller. So after t rounds, I will have groups of size 2 to the power of t. How many? Well, n divided by 2 to the power of t rounded down. And one group of size n mod 2 to the power of t. How many tries I used for each group? It is number of pairs from those elements. Power of t times 2 to the power of t minus 1 divided by 2 plus something small here. N mod 2 to the power of t times n mod 2 to the power of t minus 1 divided by 2. How many tries did I have like before doing this last round? Before that, I had groups of size 2 to the power of t minus 1, and there were before I had n divided by 2 to the power of t minus 1 rounded up groups. And since I didn't find the answer yet, it means that in each group there is at most one working battery, so A is bounded by n divided by 2 to the power of t minus 1 rounded up, which means that the number of tries I have is at least n square divided by n divided by 2 to the power of t minus 1 rounded up, and all of that rounded down. Uh, okay, first let's do some crude approximations. Let's ignore all surroundings. Like all surroundings here are working against us. Uh, so ignoring them is not a valid thing to do, but let's just check what will happen if we do ignore them. If we ignore them, this will be 2 to the power of t minus 1 times n. And here, if we ignore the rounding down here and ignore this thing completely, it will, like, this 2 to the power of t and 2 to the power of t here will cancel each other, and we will have, like, roughly n times 2 to the power of t minus 1 divided by 2, which is, like, a bit smaller than this. I think it should just work, and I should just implement it. Like, even more so considering that n is small, n is up to 40. Like, this minus 1 is pretty big compared to this number, which is not very big. But that is actually, yeah, it's probably not true if I have something like n33. I will have one element that is just outside of all the merging, and when I have two groups of 16, I will try to merge them, and it might happen that the only valid, the only working batteries were like this one, and this one. So A is 3, so I need to fit into like n squared divided by 3 operations, but I will try almost everything. Like, I will never try to compare this to check this one with any, and like, I will try all the pairs here until, like, eventually with the last pair I will find this one, but it will take me like n minus 1 times n minus 2 divided by 2 twice, which is more than this. Okay, so, like, probably, like, the general vibe should work, but if I'm getting like very skewed in the end, it will be bad. So maybe, like, instead of doing those powers of 2 and the remainder, I need to, like, split as evenly as possible. It feels like I can't give like good estimations on paper. Like, it's way to like, there's many like things that are specific for integers, like I will have those like rounding down, rounding up, and it will mess up everything. It will mess up everything. Another way to implement that is to say like I have some groups initially, and I'm just taking two groups. So initially all the groups are of size 1, and I'm maintaining invariant that in every group all the pairs inside that group are checked. And so in every pair there is at most one working battery, and then I'm taking two groups, checking all the pairs between those two groups, and then merging them. If I always take two smallest groups, it's probably like more or less optimal. I will not have a situation like this, because like instead of merging those two groups, I will merge like big one with a small one. And I will not reach this situation in the first place. It will make sure that the sizes of all groups are in ratio at most 2 at any moment. Maybe that's enough. Okay, well, I will make one last attempt to prove that that way of implementation works. And if it doesn't succeed again, I will just write it, because I believe that it is true, but would like to be able to prove it. So the way I want to do it is to look what happens when I have k groups and I merge two smallest of them. So let's say that their size is S1 and S2. And I know that those values are the two smallest values among those k groups. The total size of all groups is n. So I know that S1 is at most n divided by k, and S2 is at most n minus S1 divided by k minus 1. I will have roundings down here, but I don't want them because they make it harder to see what is going on. So I will just say that I will leave it without rounding down. And so the number of checks I'm doing here is like I need to check every pair, one from here, one from here. So the number of checks in like when I had k groups is S1, S2, which is bounded by n times n minus S1 by k minus 1. Um, okay, no. Because I still have s minus 1 here, that's not very useful, but I can say that it's bounded by s1 times n minus s1 divided by k minus 1, and this thing will increase if I increase s1 until it reaches n over 2, but it will never reach n over 2 because it is smaller than n over k, so its maximum is actually achieved when s1 is equal to n over k. So this is bounded by n over k times n minus n over k by k minus 1. Here we will have n times k minus 1 divided by k, and it will k minus 1 will cancel out, so this is n squared divided by k squared. So the number of operations I will spend to arrive at this to arrive at the state with k minus 1 groups, so like after this merge, is so like I will spend cn on the first merge, then cn minus 1 on the second, cn minus 2 on the third merge, and so on until ck, so it's sum from k to n of ci, which is bounded by n squared divided by I squared. Okay, I think I should be able to work with that more or less. So if I replace this denominator by I times I minus 1, I will make it bigger. So I make the denominator smaller, so I make the fraction bigger. Now this I can rewrite as n squared divided by I minus 1 minus n squared divided by I. You can check that the difference of those two fractions is actually this one. And now if I look at this sum, it will be like n squared divided by k minus 1 minus n squared divided by k plus n squared divided by k minus n squared divided by k plus 1 plus n squared divided by k plus 1 minus n squared divided by k plus 2, so on, plus n squared divided by n minus 1 minus n squared divided by n. So all of those things will cancel each other out, and we will be left with n squared divided by k minus 1 minus n. Which is not enough. If I had like n squared divided by k here, that would be good. probably the accumulated effect of all the estimations I did is too big for me. Well, okay, I don't see how to fix it. Actually, probably, mm, probably this algorithm just isn't good, and you need actually to split uh, in the middle, and then like each part recursively. Because like if I arrive at 3 components of roughly the same size. I guess it is possible that I will spend too much. If I have 3 components of size and divide by 3 each, and then I merge those two, the number of operations I have spent will be and divide by 3 times and divide by 3 minus 1 divided by 2 plus 2 and divided by 3 times 2 and divided by 3 minus 1 divided by 2. And like with the last of those queries I will find 2 out of 3. So if I just count this will be okay, it's like 5 by 18 and squared, which is okay, this is good enough. Okay, so okay, this is good enough. How can I show it in the general case somehow? If I have sizes sorted and I know that sk is at most 2s1, also I know that the sum of all sizes is n, and I want to give an upper bound on the sum of choose si2. I will upper bound it right away by 1/2 of sum of si square. Now I want to find what is the maximum value of sum of squares of some set of numbers with sum n if I know that they're all different. Maximum divided by minimum is at most 2. Is it enough to just say that the minimum is at most n over k, which means that the maximum is at most 2n over k, so the sum of squares is at most 1/2 times the sum of si times the maximum possible value. So I can take this out, the sum is n and this is n square over k, and square over k is not enough. Oh, come on, I need n square over k plus 1. I can actually get it, right? I can say instead of this that uh, sk is at most 2si for every I, so si is at least 1/2 sk, so the sum of all si is at least, so sk I will leave by itself, and all others I will estimate from below as 1/2 sk, so it will be k minus 1 over 2 sk, which is k plus 1 over 2 sk. This is the k plus 1 I needed. So I know that this is n, so sk is at most 2n divided by k plus 1 instead of divided by k here, and now k plus 1 and k plus 1 here. Okay, I proved it. I could have written it like half an hour ago, but this is more fun. Also, I feel like very stupid. Okay, so this actually works, and I can finally go back to competitive programming. My keyboard has gone to sleep because I haven't used it in long. That's fine. So I will have my groups, they will be stored in this vector, and I will have a set of those groups that is sorted by the sizes of the groups, and so I will have a set of pairs, size index of the group, they will be sorted by the size first, and while that set has at least 2 elements, I will take 2 elements with the smallest size and merge them by querying every pair like in between them, then merge them and put the new resulting group back into the set. As I said in the very beginning, this is not an interactive problem. Like, it is technically interactive, but you actually just need to construct a sequence of pairs you will be asking. Because like, once you receive non-zero answer, you are done. So you can just assume that you will receive 0 answers as long as possible. So like, you do not receive any information from the interactor, basically. You only receive the information you want. Great. So I will construct the sequence of pairs I'm asking. While I have at least 2 elements, taking the smallest one, erasing it from the set, then taking the second smallest, erasing it from the set, then doing the merging. And inserting the new merged group back into the set. AV size V. So now I have the set of all pairs in some order. Those must be all pairs, so I can assert that the size of this vector is and choose 2. And now I'm just iterating over all the pairs. How does interaction work? Just printing. Okay. Yep, not break, but reject. For interactive problems, I like to make sure that it passes the sample, because like sometimes you mess up the interaction protocol. Usually it will fall on sample in that case. Okay, we have 2 more problems, and obviously not enough time because I spent some insane amount of time on actually proving that the solution will work in needed number of queries, even though it is not needed to get the problem accepted. Although, like, my first version of how to implement it wouldn't work. Okay, I will probably read both problems and see if I can choose one that I like. Problem E, Mimo and Yuyu. Mimo and Yuyu just finished their 1000-piece jigsaw puzzle of beautiful Bella Arte. I don't know how to pronounce that. Now they are looking for other ways to entertain themselves. There is an n by m grid of cells with columns labeled from 1 to m, from left to right, and rows labeled from 1 to n, from top to bottom. Let UV denote the cell in the u's row and m's v's column. It's like they want us to construct the bipartite graph on vertices, rows, and columns, and cells corresponding to the edges. Because like, why would you use u and v instead of x and y? Each cell can contain any number of tokens which are indistinguishable among themselves. Initially, there are k tokens, ice of which is located in xi, yi. So they do use x and y, but not here for some reason. Oh yeah, probably they were told like that the same things like, you cannot use the same name for two different objects. Okay, whatever. Mimo and Yuyu now play a game alternating turns. On his or her turn, a player chooses a token C currently in the grid, as well as a sequence of distinct cells of length P at least 2, such that the following conditions hold. C is located in the first cell. For all I, the cells are neighboring. That is, adjacent cells in the sequence must be adjacent in the grid. Okay. B1 is at least B2 is at least BP and so on. So by Y we are moving like decreasing coordinates, so I'm assuming we're moving left. That is, the columns of the cells of the sequence must form a non-increasing sequence, never stepping away from column 1. What does that mean? Okay. Away from the column 1 means like do not move to the right. Okay. BP is 1, that is, the last cell of the sequence must lie in column 1. B1 is greater than B2, so with the first step we must move to the left. Particular B2 is equal to B1 minus 1, that is, A1 B1 must be the only cell of the sequence line in column B1. Okay, so we take some token and then we choose some path from its position to the leftmost column. We cannot move to the right, and the first step must be to the left. Okay. Then he/she removes C from the grid and adds one token to all the cells on this path. So concludes his or her turn. The player who cannot make a turn loses. Mimo goes first. Determine who will win if both players play optimally. Okay, so right now this seems like a pretty standard grindy game. Like for each cell we need to determine its grindy value. Like the moves are like all those sequences. We need to take XOR of all the grindy values of those cells and then take max of all the possible moves. Except that there can be a lot of possible moves, but I'm assuming it's still like you still need to somehow do that. Maybe it's not easy. Blah blah blah. For example, blah 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 blah. N and M and K are up to 200,000. So like even the grid can be quite big. That's interesting. It's granted that the sum of K, so the number of initial tokens, so like the size of input, does not exceed 200,000, but sum of N and M is not bounded, other than the fact that N and M are bounded, and like N times N can be very big. Well, in contest, I would probably try to like quickly write some brute force to look at the grindy values. It would be like exponential, but that doesn't really matter, right? And like see what are the grindy values, and then try to guess the formula from the, for the grindy values, probably. But like that doesn't really make sense in the video with commentary. I mean, it is the correct way to solve this problem. So maybe like it would be educational to look at that, but I don't want to do that. It doesn't sound fun. I will read the problem F instead first. Problem F: Juan's colorful tree. Juan has a beautiful tree with n nodes numbered from 1 to n. There are also k distinct colors numbered from 1 to k. Each node u in the tree has its own set cu which contains colors. Okay, so each node has some colors. Denote as let's denote with S the quantity sum of sizes of those sets. Okay, there are q queries where you will be given nodes u and v. Let P denote the set of all nodes in the simple path between u and v inclusive. You ask to calculate for each query the following quantity: the size of intersection of all the sets on this path. In other words, calculate how many colors appear in every set on the path from u to v. There are no updates. Just have a tree. We have some queries. Queries are offline. In every node there is a set. We want to find the size of intersections of those sets on a path. My first instinct is to do some centroid decomposition. Then like from centroid to every vertex I can just find the intersections. If we don't care about the number of logarithms in our solution, let's just say that we store in the set the current intersection. And then for every vertex, you can just look at all the colors that are in that vertex and check if they were in the intersection for the parent. Like we will look through every vertex just log n times, so that's kind of fine. And then for the query, if the path goes through centroid, I just need to take intersections of those two calculated sets. But that is not that simple. what else could I possibly try to do? Like for every color, look at all the vertices that have this color, find connected components on them, like the total size of those connected components will be limited. Then like for a query, I can quickly check if a given color is in the answer, if it is present on all the vertices on the path. That just I need to check if those two vertices are in the same connected component according to that color. Maybe like for a query, I can find the vertex with the smallest number of colors on the path, which is just like a minimum query on a path. It can be done with some binary jumps. And then for that vertex, I can iterate over all the colors that it has. And for each one, check if it is good. That's like obviously bad if I have a lot of short queries. But if I just memorize the answer to the query, maybe in total it cannot be very big. Like it feels like it should be bounded by n square root n. I can even like do that offline. Like first, like unique all the queries. Then for every query, find the vertex with minimum number of colors on the path. Then write down a list of queries for every particular vertex, then iterate over all the colors one by one. For all the colors, like I will write down all the vertices that have those colors, find the connected components on those vertices in size proportional to the number of vertices with those colors. And then for every vertex that has this color, like run through all the queries. So like I will have linear memory other than the binary jumps that are kind of independent from all of that. So like it will be linear memory, and the checking of like color and query is just lookup of two array values. So if it is true that the total number of colors over like the minimum vertex on the path over all different queries, if that is bounded by some kind of n squared to n, then this will be the complexity. Like it is multiplied by like 2 lookups in the array of linear size. So that should be super fast. If it is true about the property that I want. I also need to be slightly careful in the implementation. If I have a vertex of a large degree in which there are a lot of colors, like the simplest implementation I would do would like iterate over all the neighbors for that vertex for every color, which is already slow. So I only need to iterate over neighbors that have this color, which is not that simple to do. Well, I guess I can, like, for every edge of the tree, I can intersect the sets. If I root the tree somewhere, I can intersect in time proportional to the size of the like number of colors in the sun, which is linear in in total over everything. And then I will have colors on edges, and then for every color I can have a list of edges that exist in this color, and only do the like the DFSs on those edges. Then it will be linear for the construction part. Okay, in contest I would write that. I believe that the total number of colors over all distinct queries will be small enough. And I think this should work more than fast enough. But I don't have enough time, obviously. Have 11 minutes. I can think about how do grindy values work for this problem. Okay, so for the leftmost column, the grindy values are zeros because we can't make any moves here. For every value in the first column, the grindy value is 1 because like from here we have to move left, and then something but XOR of zeros is just 0, so the only possible move is to state with grand value 0, and therefore max is 1. So those are all ones. Okay, for this, like I'm assuming that borders are actually important, because otherwise only we would only have the same values in every column. So if I'm far away from borders, I'm going here, and then I can go up, or I can go left immediately. So I can either get 0 from this column, or I can get 1. So this is 2. As they just powers of 2. If the width of this field is at least 2, then yeah, it feels like those would be just powers of 2 everywhere, because for every cell, like I can move to the left, and then if I want to take this value in the XOR, I just move to the left again, or I can move down, then kill those 2, like their XOR is 0, and then move to the left. So if the width, the height of the field is at least 2, then the grand values are just 0 and then powers of 2. And if it is 1, then we don't have those choices, so like we have to move to the left immediately. We just have like this. Actually, it won't be 2 here, it will be 0 here. And then it will be 0 everywhere. Yeah, it seems that way. Okay, so it's 0, 1, 0, 0. Okay. I can write that in 6 minutes. NMK. N is this. Okay. Did D actually pass? Didn't check. Okay, so if n is 1, then I'm just interested in the parity of the number of values in the second column. So if it is 1, then the first player wins, which is Mimo. Otherwise, the second player wins. Okay, otherwise, so the XOR is 0 if and only if for every column except the first one, the number of tokens is even. I guess I can just have a set. Okay, yeah, that's easy. So if it is 1, then we don't do anything. Otherwise, if it is not in set, we insert it in the set. Otherwise, we erase it from the set. If not static empty, first one wins. What a weird problem. But maybe I'm wrong. Maybe it's not that simple. Maybe it is that simple. Okay. Is it my internet or Kidforce? On what end is the issue? I feel like 600 is not that many for such a simple problem. I mean, you do need to know like Grandi theory. And if I'm assuming that my solution is not intended. Maybe it's not even correct, but I feel like it should be. Like, I expect that there is something more interesting. But maybe still square tab. I don't know. Maybe not. Square tab ideas seem to be like kind of natural for that problem. Alright, I spent an hour trying to prove that my solution of problem D works. I hope that was at least entertaining. Thanks for watching. Bye.